All right, in this video, we're going to look at how we determine this idea of equivalent resistance in a series or parallel circuit. So we're going to start with our basics. Here I have Ohm's law. Delta V, the change in voltage from across a resistor, is the current through it times its resistance. So if I have a single resistor circuit, my simple circuit here, where I have the batteries adding a voltage V, then the resistor needs to be taking that away. Given my conservation of energy rule, I could say that this current I is just this V, because I'm changing it by that amount here, divided by R. Or if you wanted with numbers, if I say this is 10 volt battery, 5 ohm resistor, the current it's a change of 10 over this resistor, so the current is 2 amps. Now, what happens, what can I do with multiple resistors? Because now, well, I am no longer getting the total change of V over a resistor, right? I'm gaining V here. I'm losing some amount of it, and then I'm losing the rest here. So how could we figure out a way to turn this into our combination, call that R12, such that it's easy to find, it's easy to find this potential difference, and thus easier to find exactly what this current is. One thing to note when I did this, if I look at the start of this resistor, the end of this resistor, I'm going from that blue to red. So I've eliminated this purple bit, which I didn't know about. I do know what blue to red is. I know it's the voltage of the battery. And same loop, same I. So how can we do this? Well, let's use our rules. Our first rule is conservation of charge. The same amount of current is going to anywhere in this circuit. It's one loop. The current doesn't split or anything. So if I have 2 amps, 2 coulombs per second going through here, then it's 2 coulombs per second here, 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 anywhere in this circuit. So what that means is these resistors, the current through them is the same. The current through resistor 1 is the same as the current through resistor 2, which is the same as the current from the battery. Same current everywhere. My second rule is that energy needs to be conserved. Whatever the battery is adding, these two resistors together need to take away. And then I have Ohm's law, which tells me delta V equals IR. So that's delta V1 would be I1R1. Delta V2 would be I2R2. Okay, so, and in this case here, delta V would be IR12. And in this case, delta V is just V from the battery. So how can we get and relate this to these? How is R12 related to R1 and R2? I'm going to start here. I'm going to start with this idea that the battery potential has to equal the potential taken away by both resistors. And I'm just going to plug in what I know about these two things. So I'm going to take this, I'm going to put it in here, I'm going to take this, I'm going to put it in here. So this here. And let's see what happens. So I get I R1 plus I R2. And I've dropped the subscripts on these I's because, as I said here, they are equal to each other. So now I have V equals IR1. So I can just call that I, V equals I, R1 plus R2, a little distributive property here. All right, so these are the same thing. I've just taken the I out. And I'll notice, well, V equals I, R1 plus R2. I said here, V equals I, R1, 2. Well, these are both equal to V from the battery. So if I take those together, I can say I R1 plus R2 has to equal I R1, 2. And then I can cancel these I's. And I get R1, 2 equals R1 plus R2. So for this series case, we have found the equivalent resistance of R1 and R2 together is just the sum of the two resistances. And you could do the algebra if you wanted to show it to yourself, but so in series, if I want to combine resistors in series, and resistors are in series, by the way, when they have the same current through them, right? That's what we use to make all this happen, this idea that they share a current is equal to the sum of all the resistors that are in series. No matter how many they are, this will work out. Great. Well, now let's look at the parallel case. All right, so in this case, I have this parallel circuit where these resistors are in parallel. They are in parallel. Let's look at the definition of parallel again real quick. Because they both experience the same change in voltage. They are both, batteries adding V, they're both taking away V. That's what makes them in parallel. And I want to, again, somehow turn them into this situation where I just have a simple circuit with current I going through it. Okay. And one resistor, and it's somehow a combination of the two resistors. A couple things to notice. Now they experience the same change in voltage. That was not the case up above in the series. And we no longer have just one current. This I needs to split into I1 and I2. So let's write down some things we know. Well, we know delta V1 is the same as delta V2. So this resistor changes at the same amount as this one. And that amount that they change it has to be V, because that's the same the battery adds. Either resistor takes away depending on which way the charge moves. All right, what else do we know? Well, we know conservation of charge says the total I in has to be equal to the total I out. So I has to be I1 plus I2. So this I, it splits into these two, then they come back together. They have to add back up to I. So let's see if we can use these two rules to come up with an expression for this simple circuit where delta V, in this case just V, because they're changing by V, has to be I R1, 2. So basic Ohm's law for this basic circuit changes it by V. We get this relationship. All right, so again, let's start by writing Ohm's law for each one of these. Delta V1 has to be I1 R1. Delta V2 has to be I2 R2. All right, and then we can say, because of what we said here, well, that's just V, and that's just V. All right, so let's do some substitution. I'm trying to get R1, oops, trying to get R12. How does it relate to R1 and R2? So I want to somehow get rid of these I's and V's and all that and just get R1 and R2, just like here I was able to get just this. All right, well, I see this equation has I1s and I2s, so let's start there. I can write I1 as V divided by R1. So I'm just moving this R to the bottom. Let's draw that. So I can divide by R1 and divide by R1. So these ones here will cancel. I get I1 equals V over R1. Same deal here. I can get I2 equals V over R2. And I can plug that in. I can take that I1 equals V over R1, and I can put it in here. And I can do the same for I2. So I can now get I equals V over R1 plus V over R2. All right, and this is my goal, is to get this, so I can rewrite this one. Same idea. I is V divided by R1, R2. So V for R1 plus 1 over R2. So in this theoretical circuit, this theoretical resistance, R12, where it's a simple circuit, I should get this current that's the same as this current, and therefore this should work out. Oops, I forgot the V's on these. Just jumping ahead of myself. These are all the same V, because in all of these, they're dropping the same thing that the battery is adding. Well, now they're all multiplied by the same thing on top, so I can just divide out all these V's. And I'm left with 1 over R12 equals 1 over R1 plus 1 over R2. So this is kind of strange looking equation, but that's what ends up getting for a parallel circuit. I can pretend these two resistors are one resistor, and this is how I would find its equivalent resistance. So parallel 1 over Req, the equivalent resistance of resistors in parallel is this relationship. There's no easy way, I can't say. It's just the sum of the resistances upside down. I don't know. Excuse me. R3 plus, and I would go on and on if I had more resistors all in parallel, all changing the voltage by the same amount, same potential difference. Key concept here is mathematically, this number is always less than either of these two numbers. So the equivalent resistance is always less than any of the individual resistors. We could see that with this case of just two resistors. I could say 1 over R12 equals, if I want to get these a common denominator, this one could be R2 over R1, R2. So I just multiplied the top and bottom by R2 plus R1 over R1, R2. So here I just multiplied the top and the bottom by R1. And that gives me R1 plus R2 over R1, R2. Flip both sides. R12 equals R1, R2 over R1 plus R2. And this value will always be less than either one of these. You can try just plugging some numbers in here and you will see that that is the case for that. All right. And the way conceptually that makes sense is by adding resistors, I'm adding more paths in parallel. So more paths means I can get more current. Add another path here, now I get more current out of the battery. Add another path, I get more current because the current from the battery, is adding up to these currents. Which means if I want to pretend it's one resistor, well, in one resistor to get more current, I need less resistance. All right, cool. Peace.